So, all right, I'm going to give you some notes here. We're going to talk about modeling with differential equations. What's a differential equation? It's simply an equation that's a derivative. Okay? When we say something, if A is proportional to B, then what we are saying is there is some constant that we call K that is multiplying B. And K is a constant. It's often called the constant of proportionality. Let's see if I can write that. We also have something called inversely proportional, or proportional to the reciprocal. And when we say A is inversely proportional to B, we're saying that we're still going to have this constant of proportionality, but B is going to be in the denominator. So K again is a constant. Your variables are A and B. So let's take a look at this, writing a differential equation that describes the relationship. If necessary, use K as a constant of proportionality. All right. So we're going to talk about the rate of change of y with respect to x. So when you see the words rate of change, we're talking about a derivative. And the respect to x will tell you what variable you're going to have in the denominator. Sometimes it says respect to t, sometimes it says respect to some other type of measure. It may say theta down the road. So it says it is proportional, so I'm going to have that K, to the product of t and the rate of change of w with respect to x. So the only constant there is K. So again, we had those words rate of change of w with respect to x. This will always be your denominator. All right, we have the force of a spring on a trampoline can be related to the distance d if it is stretched. Weren't you guys doing things in physics with springs? Yeah. The rate of change of the quantity f with respect to the distance. All right. Alexis, how am I writing that? That's a lot of words. Rate of change of the quantity of f with respect to the distance d. Just there.
So would it be d of f over d of x?
D of f over what?
D of x? Oh no, d of d.
D of capital D, yeah. That's not my favorite thing to have two D's, but that's what we're going to do. Now, is equals. Okay, Walker, inversely proportional.
It's the division one.
It's the division one. What's on top?
Is it K?
It's K. Okay?
And then on the bottom is the ln of D.
And down on the bottom, it's the ln of D. Perfect. So we set that up perfectly. Now they give us some information. So they want us to find, it says, if the rate of change of F is 3 units per centimeter, then the spring has been stretched to 0.2 centimeters. What is the differential equation in this situation? Well, we have the differential equation. We're just missing what?
The other, like, derivative thing, like, is dw.
Well, we're going to keep this, okay? Because that's a differential equation because it's a derivative, right? But we're missing something. Is f a variable? Yeah. Is d a variable? Is k a variable? No, we gotta know what that constant is. Okay, does that make sense? All right, so, Leisha, df dd, am I given a rate?
Yes.
What is that rate? 3 units per centimeter, so I got 3 right here. Isn't that amazing that almost every single problem I've ever given in the last 2 years, there's always a number 3 in that. Equals K, right, Leisha? Over what? Do I have a length? 0.2 centimeters, so 0.2. So that means that K is equal to, is approximately, because you're going to use your calculator, 3 times the natural log of 0.2, and I did that for you guys already. Hopefully I typed in my calculator correctly. That's always the thing. I believe it's a negative. Am I right?
Yes.
4 following it? Okay, then I'm okay. 0.828. So, df dd is equal to a negative 4.828 divided by the natural log of d. This is called a particular differential equation. This is called a general differential equation. Ethan, why do I call the one on the right, lower right, particular, and why do I call the one in the upper left general?
Because the general can apply to more than one if you have different numbers.
Correct.
Particular only applies to that one.
Right. I would say you're exactly correct. I would say, hey, I don't know K here, that's why it's a general. I know K here, that's why it's particular, okay? But you are right. This one was only gonna work with this situation, right? Alrighty. This person named Mr. Brust is swimming in a straight line across a lake. His position from a point is given by P of T, where T is measured in minutes since the start of his swim. During the first 30 seconds, I always underline stuff. Because those aren't the same units, are they? Okay. During the first 30 seconds, Mr. Brust's acceleration is proportional to the cube root of the time since the start of the swim. Write a differential equation that describes this situation. Position, acceleration. P of T is position. I want acceleration. Position is not a differential equation. Acceleration and velocity are, right? Because they're derivatives. Matthew, what derivative is acceleration?
The second.
The second. So I could say I can write it this way. You might see it this way also. Either way is okay. I'm going to write it this way. Equals is proportional. What's that mean, Matthew?
That it's the constant
Right, I need that k, don't I? To the cube root of the time since the start of his swim.
So times the cube root of t.
Now, during the first 30 seconds, this only holds true, right, for the first half minute? There isn't any, like up here, I was given numbers between, here I had a rate and I had a distance, and I had a rate and I had a distance. Here, I don't have an acceleration, do I?